Assalamualaikum and a very good day to the honorable judges and everyone watching. My name is Muhammad Iman bin Ahmad Maulana, a final year student from the Faculty of Built Environment here at the Perlis branch. Today, I am thrilled to present my research project titled Integration of Earthwork Volume Calculation and Random Forest for Landslide Susceptibility Mapping at Gunung Lanno, PERAK. In this presentation, I will demonstrate how we can move beyond traditional hazard models by mathematically quantifying the impact of human activities on slope stability. So, for this slide, it is a background and problem statement. Let's start with the context of our study area. Gunung Lanno is a unique and prominent karst landscape. However, it is also a highly active industrial zone driven by extensive limestone quarrying. We know that landslides are triggered by natural factors, but recently, these risks are heavily excavated by anthropogenic or human-induced activities. When we cut into slopes and perform massive earthworks, we fundamentally destroy the landscape's natural equilibrium. This brings us to our main research gap. Current susceptibility models usually focus heavily on natural factors like rainfall or soil type. When they do include human activity, it is often just treated as basic categorical data, like labeling an area simply as forest or quarry. They fail to represent the physical, non-linear interactions of the missing Earth. My research addresses this by asking, what if we actually measure the volume of the Earth we move and fit that into a machine learning model? To solve this, the study was guided by three core objectives. First, to quantify the exact earthwork volume changes in Gunung Lanno using a multi-temporal DM differencing technique. Second, to develop a robust landslide susceptibility map or LSM using the random forest machine learning algorithm by integrating this earthwork volume. And third, to evaluate the model's predictive performance and deeply analyze how these volumetric changes influence landslide occurrences. Moving on to the methodology, our workflow relies heavily on automated geospatial processing. For data acquisition, we didn't just download data, we utilized Google Earth Engine's JavaScript API to script and process multi-temporal elevation datasets, specifically extracting the SRCM and Copernicus DMs. Next, we perform pixel-by-pixel DM differencing in QGIS to extract the earthwork volume. For the predictive modeling, we didn't just use standard built-in tools, we execute coding scripts. To train our random forest algorithm, we programmed the model to process the integrated volumetric and topographic datasets, allowing the algorithm to learn the non-linear relationships and automatically classify the susceptibility zones. Now, let's look at the results. As you can see, inside the red boxes highlighted on the slide, the high to very high susceptibility zones are critical. Looking at the area distribution table, 36.6% of the study area falls into these severe categories. Especially, these red zones perfectly outline the steep rock faces and the active quarry walls, proving that the highest risks are concentrated exactly where intensive human excavation has occurred. Regarding the model's performance, our programmed random forest model achieved an outstanding 100% overall accuracy and a perfect ROC-AUC value of 1. The mathematical distinction between artificially excavated quarry walls and untouched flat terrains is so precise that the algorithm successfully separates the classes without error. To conclude, this study has successfully achieved all its objectives. We successfully derived anthropogenic earthwork volume metrics via DEM differencing. We seamlessly integrated these volumetric changes with traditional topographic factors. And most importantly, the evaluation confirmed that human terrain modification is not just a secondary factor, but a critical, measurable driver of landslide potential. The implications of this research are significant. It provides local authorities, such as the Department of Minerals and Geoscience (JMG), with a high precision, evidence-based tool for slope stability monitoring. Ultimately, this framework enables safer, more sustainable land use enforcement in active industrial zones. That brings me to the end of my presentation. I would like to express my deepest gratitude to the Faculty of Built Environment of UiTM Police Branch for their support in and guidance for completing my research. Thank you to the judges and everyone for your time and attention.